Hi, this is Aaron with iBoard Repair, and today I'll be recovering data from an iPhone 16 Pro Max that fell in the pool and never worked again. I have it opened up here. Here's the motherboard. In this video, I'll be showcasing the damage that occurs to the motherboard when it is exposed to water and the microsoldering repair process that I'll be taking in order to fix it. Here's the motherboard taken out of the housing. We have quite a bit of corrosion on the surface layer in a few different areas. This is the RF board. This is the CPU board. The CPU board is what matters. The RF board, when we're dealing with water damage, will be completely replaced with the donor board, as it's not important to access the data. All it does is give us service, which we don't necessarily need for data recovery. Let's remove the shield so we can see underneath. And there's a very specific way you're going to want to do this. If you're using wire cutters, that is. I always start right here. And then right here, there's a couple of capacitors that might be damaged, but it's the least important. Looks like I got one of them. It's the least important area, and doesn't matter too much if I lose one of those caps. You have to watch out for the corner of NAND here while you're lifting this part, so I'll kind of lift this side a little bit more first. Allows me to get around that corner. And once this is kind of detached from the actual board, it comes up a little bit easier, which is why I work one corner at a time. So now I don't hit that little component there. And this corner, there's not too much here, so you don't have to worry too much. And then on these two corners, it's the easiest to damage. You have to be very careful on whatever one you choose. And you want to try to lift straight up instead of trying to pinch it or grab it or do very much there. And on this one, I'll just wiggle it with outside pressure until it comes off. And in that way, I didn't damage any of these components. And actually, it looks like there was no water damage or corrosion underneath the shield anyway. But now that I have access to some more components, let's test to see if VDD main is short. And I very much expect it will be, and we'll have to split the layers of this motherboard next if it is. And sorry if I was a little bit out of focus, I may have been. So I can test to see if I have a short on main right here with my multimeter. And if we look at the value on my multimeter, we can see I do not have a short. 0.3 is normal on this line. And what I can do is take my DC power supply probes now and give voltage to the battery connector, and we can see what the phone wants to do. And I am seeing an immediate amp draw as soon as I touch the battery connector, which shouldn't be there. That should only see an amp draw after I tell the phone to turn on. But it doesn't look like a full short. This looks more like a shorted button, a shorted power line. It looks like a button press, like the phone is holding down the power button. That's why it started on its own, but doesn't look like a main short. And that makes a lot of sense because we did have a lot of corrosion in this area here, and this pad here. This pad is connected to the power button line right here. It's the same line, so a good diode mode measurement there should be the same as what's on the line itself. Let's just double check that, 0.83, 0.83 of course. And I'm wondering if I'm getting no voltage on that line, because if I don't have voltage on the line, it acts as if it's a button press. It's the same thing. It's interpreted the same way, at least. So the way the button press works is you press the button and it shorts the line to ground, and shorting it to ground brings the voltage to 0, and that's what the CPU interprets as a button press. But if you're also just missing the voltage, then you're just skipping the short to ground stage, and the CPU still interprets it as a button press. So let's plug a battery in and make sure we actually have 1.8 on this line as we should. If it's missing, it might be the reason why it's prompting the phone to boot without me telling it to. So I'll plug in a good battery here. Turn our multimeter to voltage. And are we getting good voltage? Look at that. So only 0.4. So this is not getting its proper 1.8, which is why the phone is trying to turn on by itself. Even when I don't press the power button, it's trying to prompt itself to boot. And again, that's because the low voltage is the same thing as a button press. So that should also tell me that this phone should probably be giving me a repeating Apple logo. Let's just check to see if that's the case. Let's give the board good parts and see if it turns on by itself. There you go, with just a screen and a battery. It will try to turn on by itself and it will give us an Apple logo boot loop, as we can see here. And while the phone is giving us an Apple logo boot loop, if we plug in a charger, it should most likely go into recovery mode. So I'll get a charging port connected. Let's plug in the battery and it should turn on by itself again. And then if I plug in a charger, this is to a wall charger. Let's see what it does. And we go right into recovery mode. When you plug in a charger while it's booting up, while you're holding down the power button, you would normally get recovery mode, which is why we're seeing it here, because this motherboard thinks the power button is being held down. And this is all very typical of what you might see with any type of water damage that you're dealing with. So this is a very good example of an iPhone that's been damaged by water but isn't necessarily killed fully. It may give you an Apple logo boot loop and it may boot to recovery mode when you plug in a charger. So if we look at the power button line on the board view, it's right here. And there was a lot of corrosion on these test pads, and there was a bit of a corrosion bridge to the NFC F antenna negative, which I can only assume works a whole lot like being connected to ground. So it was probably constantly thinking it was being pressed and constantly being pulled down while it was wet. And the power button line, it only goes to the PMIC. So it goes through this filter here. It goes through the interposer, pops out the other side of the interposer, and goes into the PMIC. And if we think about it, what we measured was 0.81 in diode mode. And if we look at the measurement we're supposed to have, it's completely correct. So the line is not short, even though we only have 0.4 volts on it. And we also know it's not disconnected from the PMIC because we have the proper diode mode reading on it. So what does that leave us with? It could be connected to a line next to it. It couldn't be connected to a line that has a lower diode mode value because that would bring our measured diode mode value at the connector down when we took that measurement, which we didn't see. We saw the correct diode mode measurement. It could be connected to the one right next to it, but that's a 3VO line according to the name I2C, Nova, SDA, 3VO Con. So if it was connected to that line, we would see most likely a higher voltage instead of a lower voltage. If it was connected to ground on any of the pads around it, we would see the diode mode measurement drop down as well. And I'm seeing none of those things, and it doesn't do anything other than go to the PMIC. So I think the constant drain of being connected to the antenna line just killed the PMIC here. And I think the PMIC just cannot provide the voltage that's needed any longer. That's my general idea. because I was thinking, do I want to split this interposer? And then I was looking at the line and I'm not really seeing a reason why I would actually need to, according to everything I just saw and measured. So where does that leave me? Well, I mean, I could split the interposer and just go ahead and replace the PMIC, and that would probably fix the issue as well. But this is just a data recovery job, and I really don't want to do extra work if I don't have to. And it's just safer not to do extra work when you don't have to, especially when dealing with data recovery. So what's my other option? Well, we know this is supposed to have 1.8 volts and it doesn't, and that's the reason why the phone thinks it has a button press when it doesn't. So let's just try to give it 1.8 volts and see if it stabilizes. But maybe we can find another line around here, a 1.8 line, and we can just make a jumper wire and supplement this voltage here, and maybe that will be good enough. And yeah, the 1V8 S2 line looks like it may work. I think it will be easiest to run a jumper from these capacitors on the opposite side, run a long jumper and just take it down over to here. And let's see if that would stabilize the phone or not. Yeah, this looks like a pretty easy access point. So I'll run a wire from here. From here, I'll run it this way, I guess, right over to here. That's not going to be too difficult to do. That looks plenty good enough. Let's flip this over. And if I take a diode mode measurement now, let's see. It should have come down quite a bit to whatever that 1V8 line was measuring. So it should be like 0.3 or 0.5 or something. Let's see. 0.3, that looks good. The next big question, if I take my DC power supply probes and touch them to the battery connector again, will I have an immediate amp draw still or not? Let's see. Unfortunately, I still do. Interesting. I thought it would work. This line that we just attached to, we can also find right here. And I'm wondering if we're getting voltage on that line. So let's measure that real quick. It's possible that line just doesn't turn on at this stage, and maybe that's why it's not helping. I do. I get the 1.8. So interesting that it didn't help. That's fine. We can just go ahead and split these boards, and maybe we'll just see some corrosion that turned out to be the cause after all. I also have an old video, I don't know, 3 or 4 years old, of an iPhone 12 Pro Max that had a very similar issue to this, and I was able to fix it by jumping to a 1.8 line. So that was the reason I really thought it would work, but it doesn't matter too much. We'll still get the data. I've got the board on my heating platform, and let's go ahead and remove it. The heating platform I have limited to, what do I have it at? 170. And I'm going to use as much heat as I want on the top, because the top board is the RF board, and I'm going to completely replace it with a donor board while I'm taking the data from this device. So it doesn't matter if it's overheated, and we'd rather overheat this side than the CPU side or the NAND side. So I'll give the top a lot of heat, and the pads at the interposer will melt much before any damage is ever going to occur to the CPU board. So I'm only seeing corrosion at like 2 points really. Right here at the interposer. and right here at the interposer. Besides that, the board looks very clean, and the actual power button line pad, I don't remember where it is, but it was somewhere around here, and it looks completely undamaged and uncorroded. Only these 2 points. Let me take a quick look at what they might be and if they seem like they are related, and then we can do some further testing. So this was main, and it was clear when I measured. These are rows and Wi-Fi. And I don't really think any of them should have been affecting the power button line. So the easiest thing I can do now is touch the line. I'm just going to touch main with voltage, with battery voltage. And let's see if we still have that same amp draw. And if we do, it would tell me that the problem remains. And I have main right here, so let's just use that. And we still have the same problem. So it's still auto booting. It still thinks the button is being pressed, and that would imply the voltage is still low. Interesting. So now I can replace the PMIC. I think I'm going to need a new hook tool. This one is nowhere near as sharp as it used to be. And there's kind of a sweet spot actually where you don't want it to be too sharp and you want it to wear down a little bit. But after too much usage, now like I'm not really able to get in between here anymore. And these are kind of hard to order because there's like a million different types, even though they're all called the same, the Keon Lee 007. But I don't know if they're all knockoffs or if they're made different or what, but they come in all different like qualities and thicknesses. And I don't remember where to get a good one at. I feel like I may have scratched the board right here, so I'll have to double check that. Because I keep hitting a snag there when I'm moving my tool. I do kind of need to make a sacrifice here. For this repair, I have to use tweezers to like yank this off of the board, and this is what they end up looking like after. Only on this CPU is this the case, or on this PMIC. So let's see if I can find my most damaged pair. This one doesn't look great. Okay, let's try to get the chip off of the board. And honestly, if it's as hard as it can be, there may be some damage to the board afterward, but we'll address whatever happens after. And maybe I'm just lucky and it will come off without too much trouble. Look at my tweezers already. The only reason I stopped on that last one was because I was literally burning my finger and couldn't take it anymore. I'm telling you, if you have not removed one of these 16 PMICs, you really don't understand how difficult it is for them to come off. I didn't want to remove these components, but I don't think I'm going to be able to get around it. I'll just pull them from a donor board afterwards. That's not to say this is going to get much easier. This is the tool I use for my CPUs, and I'm not really willing to ruin it trying to get this chip off. What should I use here? Maybe I'll go razor blade. Let's try that. I don't think I like the angle of that, to tell you the truth. What else do I got? Let's try whatever this is. Been in there so long. probably years and years. This will be as good as anything. Other PMICs, other iPhone models, they're not like this. The underfill they used on this series is much more difficult to work with than I've seen in, I think I said earlier, since the iPhone 4, I believe. This tool might work pretty well. I'm liking it so far. I hope I don't scratch the board too much. I'll take that. Some of it came off, and that's something. There we go. That could have gone a whole lot worse than it went. Let's see if I scratched the board too badly in any spots. I may have a couple scratches. Let's try to get this cleaned up. Okay, well I have some damage here that I'll have to address, and that's a shame. I probably could have avoided that spot of damage. It was when I was digging in with the flat tool. That was why I changed it. I should be able to figure that out though. It doesn't look too bad. The flat tool was good to get under it. It was kind of using this edge as like leverage. But when I switched to over here, and I was using this edge as leverage, which was damaging it. When the solder likes to clump up like that, it's easiest just to supplement with a little bit of hot air on the side to get it to continue to flow. Okay, I'm going to wick up all of this solder now to completely flatten these pads. And sometimes I'll skip this step, but right now I just feel like it will be better if everything's completely flat. Okay, it looks like I'm only actually missing one pad. And I have a nice fat via underneath it to work with. It looks like the other missing spot is either OL or it was connected to the pad next to it. So this one's missing and this one's missing. But this looks simple to address. I can probably just put a solder blob on top of here and we'll be good. I should check what line it is because I'm not actually getting any type of reading on it, but that doesn't necessarily mean too much. So the one right above it was OL, so that's nice to see. And this one here, PPVAR Baro S2, the barometer, was, barometer, do I need that? Anyways, we can see why it's OL. It's not really going anywhere besides this one capacitor. I'll just throw a little blob of solder on there and that should address the problem. It's probably may already be good as it is, but just in case, I'll just give it the tiniest little touch with some solder and try to get some solder to stick to it. That should be good. I do still have to get these components replaced. That's a little bit of a pain. Let's find where I can pull that from. I've got one here, a donor board that is. And we can pull those two capacitors. I just double checked. The big ones are not actually needed. I just need the two small ones right here. So I'll just remove some of the underfill first. Okay, this looks just fine to me. I'll go ahead and heat the board just a little bit. And I'll add a little bit of flux down, which will melt instantly because I heated it. And I had one chip left. Where did it go? That one little point that I made is making it hard to align. That's probably aligned enough. I don't think it's all the way into place yet, but I think it needs a bit more flux. Well, that should be good. So I'll just clean it up a little bit and then we can run some tests. The very first thing I'll do is I can check to see if we're still getting that automatic prompt to boot when I touch voltage to main. Perfect. Oh my goodness. Okay, what are you doing? What are you doing, phone? I don't know what this is, but let's just put it into the testing jig and check out the battery connector. Sometimes things are just a little bit weird for a moment, and then they stabilize, which is what I'm hoping is going to happen. I've got the CPU board into the testing jig, so I'll touch my probes to the battery connector again, and we're still seeing this weird amp draw, so that's not normal. It's sitting at 0.03 before prompt to boot, but let's just ignore that for now. Oh no, okay. Well, we have a shorted power rail. That might be just a solder blob somewhere. Or it could be that I didn't put this down well enough. I'm really hoping I don't have to pull up the PMIC again. The high voltage after prompt to boot, it went like straight to 0.8. Tells me I have some power rail short, so I should be able to just find a shorted power rail. Oh, main itself is partial short. It's got to be PMIC, right? What else could it have been? Let's see if I can find heat with the thermal cam, I suppose. So if I try to inject into main, we do see heat originating between those two big capacitors. That's weird. That would be about right here. But there's not much there, so surely that's not the issue, because right on the other side is this chip. And I feel like this must be the problem, but I'm not sure how this would have been damaged. Yeah, and there's clearly damage here. You guys see this? There's a chip. When did I damage this chip? Was it during the shield removal? I don't think at all I did that then. Because this chip is dead because it's cracked. And I have no idea. If you watched this video and you saw when I damaged this chip, because surely this had to have been me, let me know. I don't quite understand when that would have happened. Interesting. Well, hopefully that's it, and this is addressable still, and we'll have no more surprises. Let's take it off and replace it and see if we're good. We'll take it off, see if it clears, and then we can see if we're good after that. That is so strange. I wonder if it was at some point I hit it on the bottom of the platform I have here, the board holder. At one point I accidentally like put it all the way flat, but it wasn't like I hit it hard or anything, but I can't really think of what else would have happened here. Okay, let's make sure first that we are free of any voltage leak. I hope we are at this point because I just do. Good. No leak on main. Let's make sure there's no leak on bat either. No leak on main, no leak on bat. Good. Maybe we'll be okay after all. Let's just harvest this chip and get it replaced and see if that was just some weird little hiccup and we're actually good still. And luckily I do have one I can pull from right here. I have no idea what this chip is called. If you're an iPhone technician and you know what this chip is called, let me know in the comments. But this is the chip that creates VDD main, so it's a very important chip. And that pool looks clean enough that I think I'll just not reball this chip. And I think we'll be fine still. All right, let's get this chip soldered to the board. There we go. Okay, I hope we are ready now. Let's check for a voltage leak first. No leak. No leak. Okay. Put it in the jig and let's test the current draw next. So now once again, I'll touch my DC power supply probes to the battery connector. 0 amp draw, which is what we want before we prompt it to boot. And now I'll prompt it to boot, and what do we get? We are getting finally what looks like a normally booting iPhone. So let's plug in the parts and see if we're actually finally there. So it's not turning on by itself is the first thing to note, which is good. And when I plug in USB-C, we have an Apple logo. Also good. And it booted. Great news. So this is a good example of the type of damage that you would expect to see when your phone has been exposed to water. This one was dropped in the pool. And what I saw when it was connected to good parts was first an Apple looping iPhone. And if you were to plug in the charger while it was looping, it would move into recovery mode. This was caused by low voltage on the power button line, tricking the CPU into thinking that the power button was held down. In order to fix this issue, I had to change the PMIC, which was held firm to the motherboard with very tough underfill, which is unique to the 16 series. I've not seen this on any other models. Underfill that's so tough that is. But I'm glad this one's working and the customer will be happy to receive his data. Thanks for watching. Have a good one. Bye.